Right, morning lads. Hope you're well. We're starting a new topic today. It's not a particularly long topic, but it's a really important one because it feeds into a lot of the other topics you're going to learn as you now progress into the second year's worth of content. Materials was the last section of content, which was from this year, and now we're moving on to study the content which would usually be covered in the second year. It's really important we get ahead on this so that it means that when you come back, you were able to link your new learning to what you've learned here. And it will save time here and allow more time for revision at the end of the course, which will be really important. The topic we're doing is circular motion. Hopefully, across this lesson, it will become clear why we learn about this and why this is such an important part of physics. As we start off, I'm going to ask you to bear with me so that I can build in what you need to know about it. So, as a warm up, we've got a question which you're reasonably familiar with. So, a car starts at rest and accelerates to the right uniformly at 3 meters per second for 2 seconds. And the question is asking you to calculate the distance travelled while accelerating. In addition to doing the calculation, I would like you to do 3 other things. I would like you to think about what assumptions you've made in your answer or the method that you've used to get to your answer. Some of those, there's some words in the question which give you a clue to that. I would then like you to think about 2 other things. What can you say about the car's motion while it's accelerating? Some of that might link to the assumptions that you've said in the previous answer. And given that, what can you say about the forces on the car? So 3 things: calculation, assumptions, motion and forces. Pause the video now and have a go at the questions. Okay, so to start with these sorts of questions, familiar method, SUVAT. So we write out our SUVAT and we try and identify each thing. S, we don't know, that's what we're trying to calculate. U is going to be 0 as the car starts from rest. V, we don't know, no information given in the question. We do know that it's accelerating at 3 meters per second squared. And the time is for 2 seconds. You then go to your bank of SUVAT equations, and the one that you will pull out is S equals UT plus a half AT squared to find the S. Really helpful, by the way, if you know these equations off the top of your head and you don't have to look back in the formula sheet. We substitute the numbers in. Our U is 0, the car's at rest, and that means we're just doing a half times by 3 times by 2 squared, which is 4. Evaluate that, and then that will give you 6 units, be careful, meters. Standard SUVAT type question. Now, I've asked you to state the assumptions that you've made in your answer and method. What's important here, and the key word in the question that gives you a clue to this, is this word uniformly. And it's that word which actually allows us to apply this method of SUVAT equations. So in terms of the assumption we've made, we've assumed that the car experiences uniform acceleration. Let's just remind us what that means. Uniform acceleration means constant acceleration. Now, what that's saying is the acceleration for that whole length of time has been 3 meters per second, and it hasn't changed. And the assumption that links to that is, well, what is likely to cause a change in the acceleration? It's going to be something like air resistance. So in this question, we could say another assumption that links to the fact that it is uniformly accelerating is you're ignoring air resistance. Standard thing for SUVAP problems. Is it sensible to ignore air resistance in this case? We're dealing with low velocities, so it's not a horrendous assumption to make. The higher the velocity, the greater air resistance is going to have an impact. So, next thing is, well, what can you say about the car's motion? This is a bit of an open-ended question. We know the car is accelerating, and we know that it's accelerating uniformly. So everything that we've said there about uniform acceleration, constant acceleration, directly applies to the answer to that question. The other thing, which isn't obvious, or may not be obvious, is that acceleration, we're not just talking about the magnitude. Remember that if an acceleration is constant, it not only means that it's constant in magnitude, but it's constant in direction. So, in fact, we can say, in addition, what about the car's motion? It's travelling in a straight line, or accelerating in a straight line. Another word for this is linear motion. Now, without actually ever stating it before, all of the problems that we've looked at so far using SUVAPs, or even using the conservation of energy for that matter, they've all been problems where they've been travelling in a straight line. There's one exception to that, which is when we've looked at projectile motion, but the overwhelming majority of questions we've looked at, the car's been travelling in a straight line, or whatever we've been looking at has been travelling in a straight line. We haven't looked at anything which is changing the direction of the velocity, with the exception of the projectile motion questions. Finally, then, what can you say about the forces? Well, from Newton's second law, we know that if the car's accelerating, it must experience a resultant force. We can't go and calculate that force because we don't know the car's mass in this question. So we can say there is a resultant force, and this resultant force is constant in magnitude. And we can say something about its direction because the acceleration is always in the direction of the resultant force. So we can say it's a resultant force, constant resultant force to the right.